Okay, in this video, we're going to start with symmetry. And in the next two videos, that will lead us to what are called even and odd functions. Notice there's no chapter or section number with this. And that's because this comes from several different spots in the textbook. Early in chapter 1, they talk about symmetry. And then I believe it's later in chapter 2 or maybe even 3 where they talk about even and odd functions. I think that is chapter 2. And then later in the trig sections in chapters 6 and 7, they bring the idea of even odd functions to the trig functions. I like to see it all put together, because it's a good flow to go from symmetry into even and odd functions, and then to extend that to the trig functions. So this is some scattered stuff throughout the book. So the example numbers might be a little out of order. There'll be some missing. And the homework is all going to be worksheet based for this section. I just took little bits of stuff out of the book and other places I found on the internet. So first let's talk about symmetry a little bit here. Make this a little bit bigger. Graphs of equations can have symmetry with respect to one of the coordinate axes, either the x or the y-axis, or with respect to the origin. Symmetry with respect to the x-axis means that if the Cartesian plane were folded along the x-axis, the portion of the graph above the x-axis would coincide with the portion below the x-axis. So if I look here in the first graph, if I trace over this top part of the graph that's in the quadrants 1 and 2, I see here a point on that graph is x comma y. Well, imagine that we folded this like a piece of paper along the x-axis. Well, if I fold that, this part up here is going to fold down, and now it's going to land right on top of this lower piece. The function as it exists below the x-axis. And notice what happened to the point x comma y. Since I folded it over the x-axis, the x-coordinate did not change. It's positive x for both points. But the y value here in quadrant 1 was positive. As that's reflected down here into quad 4, it's now negative. So again, that would be x-axis symmetry. And something similar happens to the y-axis symmetry. Here's our y-axis. So we're going to fold our Cartesian plane along the y-axis. And of course, what that's going to do is take this piece of the graph. I'm a little off there. But we're going to take that and reflect it over the y-axis. And now it's going to land over here on top of the other half of the graph. And again, here's an arbitrary point, x comma y. Since we are folding it now over the y-axis, the y-coordinate does not change. It's still a positive y. But the negative x-coordinate has been reflected to, or this positive x has been reflected over here to a negative x-coordinate in the second quadrant. And the origin, the last one here, here the arbitrary point on the graph is x comma y. Well, if we know its origin symmetric, it's going to have another point on it, the negative of each of those, negative x comma negative y. And if I highlight this piece of the graph here in red, each of these was sort of one fold. We folded here across the x-axis. We folded here across the y-axis. Here we would fold across both axes. First if I go about the y-axis, there it is. If I folded about the y-axis, that would take me over here. And then I would fold it over the x-axis, and that would take me down into the first quadrant. Or the order, you could do them in reverse. First we could go over the x-axis, and that would take us down to quad 4. And then across the y-axis, and that would again, finish us right on top of the other piece of the graph. So origin symmetry is sort of a two-fold symmetry. And, why is this important? Well, if we know the symmetry of a graph before we attempt to sketch it, it's helpful because we might only need half as many solution points to actually make a sketch of the graph. And summarized here in the box is our graphical tests for symmetry. Number 1, a graph is symmetric with respect to the x-axis if, whenever x comma y is on the graph, so is x comma negative y. Number 2, a graph is symmetric with respect to the y-axis if, whenever x comma y is on the graph, negative x, y is on the graph. Now notice we're looking at the symmetry of an axis, and that also is the same for the point. That value of the point will not change. Like here we're looking for x-axis symmetry. Well, x is on both of these points, x comma y and x comma negative y. When we are checking x-axis symmetry, it's the other variable, the y variable, that will change from positive to negative or vice versa. Same thing for number 2. We are checking y-axis symmetry, so that means our x will change from a positive x to a negative x. If we're checking y-axis symmetry, the y-coordinate does not change. On both of these, it's positive y. Number 3 is about origin symmetry. It says if whenever x comma y is on the graph, negative x comma negative y is also on the graph. So here we got a table of values, and we also have a graph that goes with it. Okay, you can conclude that the graph of y equals x squared minus 2 is symmetric with respect to the y-axis because the point negative xy is also on the graph. And, we can see that quite obviously here in the table. If I look at these two x values, both x values are 3, but this one is a negative 3. What y values come out of the function when you plug a negative 3 in? Positive 7. What y value pops out of the function when you plug in the positive 3? Also positive 7. So here we have the point negative 3, 7, and 3, comma 7. Let's move in a point. Here is negative 2, and over here is positive 2. For the different inputs of 2 and negative 2, we have the same output, positive 2. So here's the point negative 2, 2, and here is the positive 2, comma 2. And the same thing holds in the middle there for 1 and negative 1. So we plug in a negative 1 or a positive 1, and the function spits out a negative 1. So we can see there that we do have y-axis symmetry. And, later on in this lesson, the third video, I believe, we'll come to the shortcut of how we can identify these different types of symmetry. And if we know that the graph is going to be symmetric about the y-axis, I should switch over to red here. If we know we're going to be symmetric about the y-axis, we can get away with only plotting half the points. If I know I have y-axis symmetry and I can plot the point 3, 7, I automatically know negative 3, 7 is also on the graph. As I graph and get 2, comma 2, I automatically know because of the symmetry that negative 2, 2 is going to be on the graph. And same for negative 1, comma negative 1. So here on the left or the right, if I graphed these in red and I was sure of those, and I knew my function was y-axis symmetric, I could automatically fill in this half of the graph just by knowing the symmetry and not having to plot, more points. Now, what if you don't have a graph, and what if you don't have a table? Well, luckily, there is an algebraic test for symmetry. So, number 1, the graph of an equation is symmetric with respect to the x-axis if replacing y with a negative y yields an equivalent equation, or the same equation. Number 2, the graph of an equation is symmetric with respect to the y-axis if replacing x with negative x yields an equivalent equation. I like to think about is if you're checking the symmetry of one axis, you're messing with the other variable. Here we were checking for x-axis symmetry, so we were playing with the y variable and replacing it with negative y. In number 2, we're checking the y-axis symmetry, so that means we're going to mess with the x variable and replace x with negative x. And of course, origin symmetry, we replace both. The graph of an equation is symmetric with respect to the origin if replacing x with negative x and replacing y with negative y yields an equivalent equation. Now, maybe that's a little confusing, all those words. We're going to clear this up in probably the next couple examples. We're going to do some algebraic tests for symmetry. So here in example 5, it says test y equals 2x cubed for symmetry with respect to both axes and the origin. So let's see here. First, they want us to check the x-axis symmetry. And if we're checking x-axis, that means we are going to replace y with negative y. Now, I'm going to also highly encourage you to always do your replacements in parentheses. That will maybe help minimize the chance of mistakes with order of operations. Please excuse my dear Aunt Sally. So we're going to take the equation they give us, and we're going to replace this y with a negative y. And nothing else is going to change. That's still going to equal 2x cubed. Now, in class, I'll ask my students, there is an implied exponent up here. What is it? Well, if you don't see one, there's an implied one. Negative y to the first power is just negative y, so we can drop the parentheses. And the rest of the equation does not change. Now, here we have a positive y equals some stuff. Here we have negative y equals some stuff. Well, let's, get this to be the same, and we're going to divide or multiply both sides by a negative 1. So now we're going to have y equals negative 2x cubed. So the question is our original equation equivalent to this one? Well, up here is y equals 2x cubed, and we found y equals negative 2x cubed. Well, those are not equivalent. So not equivalent, I'm going to abbreviate. Equivalent, not equivalent, and if you move on to some higher level college math classes, you might see these 3 dots in the shape of a little triangle. That's math shorthand for therefore. We found our equations were not equivalent, therefore not x-axis symmetric. X-axis symmetric. And I'm going to abbreviate symmetric, S-Y-M-M. So we did our test. We replaced the y with a negative y. We did not get an equivalent equation. Therefore, we are not symmetric to the x-axis. All right, well, x-axis didn't pan out. Maybe we'll have more luck with the y-axis, and I'll give myself a little more room here. So let's check out the y-axis. For the y-axis test, we are going to replace the x's with a negative x. And again, I encourage parentheses. So let's see what happens here. The y does not change. We changed that last time. The 2's not going to change, but here we had x to the third power. Well, we're going to replace that x with a negative x. Now it becomes order of operations and properties of exponents. So let's see what we have here. Negative x quantity cubed. That is negative x times negative x times another negative x. Well, a negative times a negative is a positive, times another negative is negative, and then x times x times x is x cubed. That is supposed to be a parenthesis there. So 2 times negative x cubed, well, that's negative 2x cubed. So we ask ourselves, the original equation is here. We have this. Are they equivalent? Are they exactly the same? No. So we are not equivalent, and therefore not y-axis symmetric. Okay, the x-axis symmetry didn't work out. The y-axis symmetry didn't work out. Maybe we'll have a little more luck with the origin. Let's try. Now, remember with the origin, it's like both tests combined. We are going to replace x with a negative x, and also, ooh, that's a terrible parenthesis, and we're also going to replace all the y's with a negative y. And let's see what happens. So this y becomes a negative y, and that's equal to 2. And then this x becomes a negative x that we are going to cube. So this is sort of like a combination of the last 2 parts of this example. Negative y, this is to the first power, so we can just drop the parentheses. That is a negative y. Equals. This is exactly like the one we just did. Negative x quantity cubed is negative x cubed times 2 is minus 2x cubed. Now the question is our original equation equivalent to this? Well, at first glance you might say no, but up here again, remember we have y equals some stuff. So just like in the first part, let's divide or multiply each side by a negative, and then we'll get y equals 2x cubed. Aha! Those are equivalent. We started with y equals 2x cubed. We did our test. We are right back to where we started. So this tells us about the symmetry. We are origin symmetric. So these are equivalent. I'll put a little equivalent yes. And what does that mean? Therefore, origin symmetric or origin symmetry. And there we go. We can test algebraically for x or y-axis and the origin. All right, a couple problems to try on your own. Now, I've seen in the past where some students will take these and maybe solve for y equals this or x equals that. That's not necessary. Just take the equation as they gave it to you. Test for the x-axis symmetry, test for the y-axis, and then test for the origin. This is a good spot to pause the video, try those practice problems, and fire it back up and see if you got the answers correct. Okay, I'm going to move this out of the way. Got a little more room here, and I guess I can put these in the garbage. All right, I guess there's no better place to start than with the x-axis symmetry. So x-axis means we're going to mess with the other variable. We're going to take all the y's out and replace all the y's with negative y's. That's not a very good exponent. So I'm taking this y out, and I'm going to replace it with a negative y. So order of operations, do I distribute the negative to the negative and go positive? No, we want to work in the parentheses and especially with exponents. So that's going to be x minus negative y times itself is positive y squared. And you can see immediately that this is exactly the same to our original function. So we have found x-axis symmetry. Yes, big exclamation point, I'm so happy. We found x-axis symmetry. Now, if you think about it, you can only have one type of symmetry, x or y or origin. So I've had students in the past ask me, as soon as I find the symmetry, can I stop and move on? If you did everything right, it wouldn't hurt anything. But let's say maybe you made a mistake. Maybe we found x-axis symmetry when it really was not. If you check the y-axis or the origin and you also get a yes answer, then you know you made a mistake somewhere. So you can always back up and look for your error. So I encourage you, and especially since this is new and we need practice, let's continue on with our tests. Let's check the y-axis. So now we're going to replace the x with a negative x. And we're going to leave the y alone. So since this is to the first power, we can just drop the parentheses. And now we have negative x minus y squared equals 0. Is that equivalent to what we started with? No, we have a negative in front of the x down here now. You can think, well, okay, maybe if I multiply both sides by a negative. If I multiply the left side by a negative, this will get switched to negative, as will this. Is that equivalent to what we started with? Well, no. Now this is a plus, where in the original equation it was a minus. So no, these are not equivalent, therefore not y-axis symmetric. Okay, we checked x. Yes. We checked y. No. Again, it's a good idea to, complete all the tests. Let's check for origin symmetry. So we replace the x with a negative x. Ooh, I don't like what is wrong with my parentheses today. Minus x. And I'm also going to replace the y that we square with a negative y and see if that's equal to 0. So first power here, negative x, we can just drop the parentheses. Minus negative y squared, we already discussed that. That is positive y squared. Is that equivalent to where we started? Close. Up here is a positive x. Down here it's a negative. We could distribute a negative, but that'll change this to a plus where it's a negative in the original. So no, we are not origin symmetric. So y-axis symmetric, yes, not the x-axis. Number 32. And make that a little bigger, cover that up. Okay, we got x times y equals 4. This isn't a too bad of a one. Let's check the x-axis. So I'm going to replace the y. This was x times y. Now it's x times negative y equal to 4. Well, what is positive times negative? Positive times negative is negative. X times y is xy. Negative xy equals 4. Is that equivalent to what we started with? No. So not x-axis. And I'll put a frowny face. But maybe we'll have better luck with a y-axis. So now we're going to replace the x with a negative x, and we're going to leave the y alone. Well, let's see here. Negative times positive is negative. X times y is xy, and that's equal to 4. It looks very similar to what we found here, but that's not what we're looking for. We wanted it to match this, so it is also not y-axis symmetric. Okay, that'll be another frowny face. And maybe I'll put a great big tear here because I think we're running out of time. Hopefully we're going to be origin symmetric. There will be cases where some functions will not be symmetric to anything, any axis or the origin. But I have high hopes here for the origin, and I hope you see what's about to happen. For the origin symmetry, I'm going to replace the x with a negative x. I'm going to replace the y with a negative y. Back up, there we go. So here, negative times negative is positive, x times y is xy, and that's equal to 4. Is that equivalent to what we started with? Absolutely. So we found it. We are origin symmetric. And that deserves a great big happy face. Well, that's not very happy. There we go. So those are the tests for symmetry. The homework is a work. Oh, no, that's right. We got one more to go here. Threw in an extra one to try on your own and then compare with the group in class. And I threw you a curveball with the absolute value bars. So as long as you remember what the absolute value bars do, you'll be fine. So first, let's check x-axis symmetry. So we're going to take the y out and replace it with a negative y. We still have our absolute value of x minus 2. So are these equivalent to what we started with? No, because now our y is negative. If I were to divide or multiply both sides by a negative 1, we would have positive y equals the negative absolute value of x plus 2. And that is very, very different from what we started with. So definitely not x-axis symmetric. Let's check y-axis. Okay, so check the y-axis. I'm going to replace x with negative x. So this will be in the bars, negative x minus 2. Okay, if we look back to the original equation, of course, the bars are going to make whatever is in here positive. So that will be y equals x minus 2. Same thing here. The bars will make what is in here positive, so the bars will negate out this negative sign in front of the x. So we could rewrite that as y equals absolute of x minus 2. It doesn't matter if it's positive or negative in here. No matter what x is, that's what's coming out. So here we do have an equivalent expression. So we do have y-axis symmetry. Just to be safe, to maybe catch a mistake if we made one, let us also check out the origin. All right, I'm going to replace the y with a negative y. And I'm going to replace the x with a negative x. So let's see over here, it's first power, so the bar or the parentheses mean nothing. Negative y equals, we could say that those bars are going to turn that x from a negative x into a positive. And we still have our minus 2. Is that equivalent to what we started with? Absolutely not. So we are also not origin symmetric. All right, well, that's the intro. In the next video, we'll get into what they call even and odd functions. The homework is a worksheet, and if you missed class and you don't have the worksheet, these are the problems from the worksheet. So you could just copy those down onto a piece of paper and solve them and hand them in, and that'll be just as good. All right, see you in the next video.